The word rain on Titan means something fell from a cloud and hit the ground and almost nothing else. Everything else the word carries the smell of it, the sound, the way it sinks into dirt, the chemistry that makes it possible to drink, the animal reflex that says find shelter. None of that travels. The word made the crossing anyway. It's worth pausing on that, because it's the kind of thing that happens so fast you don't notice it happening. A spacecraft found clouds, found precipitation. The precipitation landed on a surface that was already shaped by channels and valleys and something that looked like drainage. The scientists reached for language, and the language they found was Earth's. And why wouldn't they? The Earth language was right there, and it fit. Loosely, visibly, correctly enough. Rain fell on Titan. Channels carried it somewhere. There were seas. The question this script is pressing on is a quiet one. Not whether those words were wrong. They weren't wrong. The question is what those words brought with them, what they imported silently, attached to themselves, carried across 1.25 billion kilometers without being declared. Because words don't arrive empty. They arrive with everything they've ever meant. And when you apply them to a world they were never built for, the question isn't just whether they fit. The question is what assumptions ride in behind the fit. What you stop asking because the word already answered it. That's the seam, not in the facts. In the language the facts were given when they arrived. Start with what is actually known, and hold it separately from what it's been called. Titan is a moon of Saturn, the largest of Saturn's moons, and at 5,150 kilometers across, larger than the planet Mercury. It sits roughly 1.25 billion kilometers from the Sun. Its atmosphere is denser than Earth's, at about 1.5 times the surface pressure you're breathing right now. That atmosphere is mostly nitrogen, which is what Earth's atmosphere is mostly made of too, and that similarity contributed, early on, to the sense that Titan was terrestrial in some important way. The surface temperature is around -179 degrees Celsius. Hold that number for a moment. Your nearest wall, wherever you are, if it were at that temperature, it would behave differently than you expect. Not because it would shatter, though it would. Because water ice, at that temperature, has the mechanical properties of granite. It doesn't melt under pressure or weight. It doesn't flex. It doesn't sublimate. It sits there, structural and inert, and serves as bedrock. Titan is built on that. The mountains of Titan are water ice mountains. The pebbles on the floor of the channel where Huygens landed, small rounded shapes, a few centimeters across, showing signs of having been carried and tumbled by something moving those pebbles, are water ice. They looked, in the photographs, like pebbles in a dry stream anywhere on Earth. They were made of frozen water, not rock. Water, frozen so hard it was indistinguishable from rock. The fluid that shaped those pebbles was not water. It was methane. Methane is a molecule of 1 carbon and 4 hydrogen atoms. At the temperatures and pressures of the surface you're sitting in right now, it's a gas, what comes out of a stove burner, what leaks from a landfill, what cows produce in quantities that have become a climate concern. You can't pour it. You can't wade into it. It has no shoreline. On Titan, at -179 Celsius and 1.5 atmospheres of pressure, methane behaves the way water behaves here. It is a liquid. It evaporates from the surface into the cold air. It condenses into clouds. It falls as rain. So there's your rain. The question is what you've understood when you use that word. The rain on Titan is rare. That's the first thing the Earth analogy quietly obscures. On Earth, rain falls somewhere on the planet almost continuously. The tropics receive rain that can be measured in meters per year. The temperate zones have seasons, But even in a dry summer, rainfall has a frequency weeks, days, in some places hours. You understand rain as a rhythm, a recurring thing, background weather. On Titan, the best estimates suggest that any specific location might receive significant methane rainfall roughly once every several hundred Earth years. The figures come from combining precipitation rate models with the frequency of observed storm events and the orbital mechanics of a moon that takes roughly 16 Earth days to orbit Saturn and lives in a system where a full year takes 29.5 Earth years. Titan's year is long. Its seasons last years. When the equinox comes, the point at which one hemisphere begins passing into its long summer, the atmosphere changes in ways that can trigger massive convective storms, big enough to be visible from Cassini as bright masses moving across the disk, big enough to leave dark, wet marks on the desert like equatorial surface that Cassini could photograph before they dried. In September 2010, one such storm occurred near Titan's equator. The dark, wet region appeared and then faded. The storm had drenched what is, in Titan terms, an arid landscape, an equatorial region of enormous longitudinal sand dunes, each dune potentially hundreds of meters tall, built from dark grains of complex organic compounds called tholins that snow down from the atmosphere and accumulate over millions of years into terrain that looks, in radar images, like the Sahara viewed from a great height. That storm was noticed because the surface changed afterward. It was 2010 on Earth's calendar. The last comparable storm at that location may have occurred when the Roman Empire was still deciding what to do about Britain. The word rain doesn't carry that. When you say rain, you carry frequency. You carry the ordinary. Rain is not an event on Earth. Mostly it's a condition, a background process, a rhythm. On Titan, rain is a geological event, a century event, a climate punctuation. And the equatorial storms, the rare ones, the massive ones, are not even where most of the liquid ends up. The liquid is at the poles. The North Polar region of Titan is covered in lakes and seas, not metaphorical seas, not traces or remnants. Lakes and seas of standing liquid, filled right now, in the late northern summer. The biggest of these, Kraken Mare, has a surface area somewhere around 500,000 square kilometers, comparable in scale to the Caspian Sea, which is Earth's largest lake. The name doesn't help, actually. Calling Kraken Mare a sea or a lake is already doing the thing this script is pressing on. But call it what it is. A body of standing liquid large enough that it takes a significant time to cross, deep enough in places that radar soundings couldn't reach the bottom, and composed of a mixture that the word sea was never designed to describe. The composition of Kraken Mare is primarily liquid methane and liquid ethane, with nitrogen dissolved throughout. Not mostly methane with a little ethane, and not mostly ethane. The ratio depends on depth, on season, on a set of thermochemical interactions between these three compounds that behave in ways Earth chemistry has no direct analogy for. Ethane is heavier than methane. Methane is more volatile, it evaporates more readily. When methane evaporates from the surface of a Titan lake, the liquid left behind becomes richer in ethane, but dissolved nitrogen, which the lake absorbs from the atmosphere above it, complicates the density calculations in ways that are genuinely counterintuitive. A methane-rich mixture, at certain temperatures, can actually be denser than an ethane-rich mixture, which means that when a lake evaporates and stratifies, the layers don't stack in the order you'd expect. There can be a heavier methane-rich layer sitting below a lighter ethane-rich layer, and when that stratification becomes unstable, the lake overturns. When it overturns, dissolved nitrogen can suddenly can bubble out of solution the way carbonation bubbles out of a shaken bottle. In Ligea Mare, the second largest sea, Cassini observed what the mission team called Magic Island's bright features in the radar data that appeared in one flyby and were gone in the next. Features that showed up where no topography had been detected before. The best current hypothesis is that these were exactly that, bubbles of nitrogen gas rising from the lake bed in masses large enough to be visible to an orbiting radar instrument. An effervescence, a sea that fizzes. There is no word for that in any existing weather vocabulary. The rain that feeds these seas falls at the poles during polar summer. It evaporates and migrates, carried by circulation, back toward the tropics. But there's a problem, and it's one that cuts right through the water cycle analogy. The amount of liquid on Titan's surface doesn't balance. Earth's water cycle is a closed system. The water that evaporates from the oceans eventually falls as rain and returns. The total amount stays roughly constant. The cycle is a cycle in the true sense it closes. Titan's methane cycle does not obviously close. Methane in the upper atmosphere is destroyed by sunlight. Ultraviolet photons break the molecule apart, a process called photodissociation, and the resulting fragments recombine into heavier organic compounds that eventually snow down onto the surface as tholins or ethane, or escape into space. They do not recombine into methane. The destruction is one way. The total amount of methane in Titan's atmosphere, destroyed at this rate, would be gone in roughly 10 to 30 million years. Titan's atmosphere still has plenty of methane. Something is replenishing it. That something is not understood, not settled, not a footnote in the accepted account, a genuine open question, large enough that it shapes how you should read everything else about Titan's weather. The most plausible candidate is cryovolcanism, geological processes in which Titan's interior heat drives fluids upward through the crust and out through vents, not lava, but a cold slurry of water and ammonia, which could carry methane that was stored in the crust as methane clathrate, a kind of frozen cage structure in which methane molecules are trapped inside a lattice of water ice. When the clathrate reaches conditions under which it destabilizes, the methane is released. The evidence for this is indirect. Cassini detected argon-40 in the atmosphere, a particular isotope produced by the radioactive decay of potassium-40 in rocks, which then has to migrate from the interior to the surface. On Earth, argon-40 escapes through volcanic activity. On Titan, its presence suggests that something geological is actively outgassing from the interior. Whether that same process is releasing enough methane to sustain the atmospheric reservoir over geological time remains unconfirmed. There are candidate cryovolcanic features in the radar imagery. Sotra Patera, a deep depression with what looks like a flow feature beside it, has been proposed as a volcanic caldera. The debate over this is not resolved. So Titan has a weather system. The weather system runs on methane. The methane is being destroyed faster than it visibly accumulates, and the source that keeps it running may be volcanic, or may be something else, and has not been definitively identified. The accepted account, the one that calls this a methane cycle analogous to Earth's water cycle, uses a vocabulary that implies a closed loop. Cycle suggests return. Cycle suggests the thing comes back around to where it started. On Titan, the methane that rains may not be the methane that will one day rain again. Some of it is lost. Some of it may return from below. The accounting doesn't fully close. Go back to January 14, 2005, and press on the data the accepted account rests on. This is the date Huygens descended through Titan's atmosphere. It is the only time a human-built object has ever touched Titan's surface. It is the only time we have ever had direct measurements from below the clouds. The probe took 2 hours and 28 minutes to descend from the top of the atmosphere to the surface. It survived on the surface for 72 minutes before its battery died and the relay linked to Cassini moved out of range. Total surface contact, 72 minutes. Total surface area sampled, 1 point. A flat plain near the equator, in a region called the Adiri, scattered with small rounded ice pebbles in a dry riverbed. 1 point. 72 minutes. Every statement about what Titan's surface is like, what it smells like, what it feels like underfoot, what the subsurface moisture content is, what the organic sediment layer consists of, derives from one data column, measured once, in one location, in one season, on the equator of a world where the weather is known to vary dramatically between the poles and the equator, and between seasons that each last several Earth years. Huygens detected methane vapor in the soil at the landing site. The probe's heaters warmed the ground and the gas chromatograph detected methane boiling off. This has been cited as evidence of a damp, methane-moist subsurface, which it may be. But the landing site was selected partly for safety, not for scientific representativeness. The equatorial region is, by the best evidence, the driest part of Titan. If you landed in the Atacama Desert and found a small amount of subsurface moisture, you would not conclude that Earth was a wet world. The atmospheric measurements during descent were more comprehensive: 6 instruments operating across the full column of atmosphere, from 150 kilometers altitude down to the surface. Those measurements told us the temperature profile, the wind speeds, the methane humidity at various altitudes, the chemical composition, the haze structure. All of this was from a single vertical profile, dropping through the atmosphere at one location in what was late southern summer on Titan. Cassini, in its 13 years orbiting Saturn, added enormously to this. Its radar mapped roughly 60% of Titan's surface, finding the lakes and seas and dunes and river networks. Its infrared spectrometer reads surface compositions through methane atmospheric windows. Its radio science measured the atmosphere's structure on flyby after flyby. But Cassini was an orbiter moving at 5,000 meters per second. Its radar images, at their best resolution, were around 300 meters per pixel. It never landed. It never tasted the atmosphere directly. It looked from above and from distance and inferred. The science is real. The inferences are careful. The models have been tested against the data and refined. But the point is worth holding. Every broad statement about Titan's weather, about how the methane cycle works, about where the clouds form and when and how much rain falls, is built on a scaffolding of inference, supported by one descent profile, 13 years of orbital observation, and the computational models those observations constrain. The confidence in that scaffolding is earned, in part. But in part it is a function of the fact that we have no alternative. When there is only one data point, it tends to be treated as more representative than it is, not dishonestly. The scientists writing these papers know exactly how limited the Huygens data are. The abstracts say things like constrained by available data, and models suggest and consistent with observations. The qualifications are there, but in the popular account, the one that says Titan has a methane cycle, analogous to Earth's water cycle, that it has rain and rivers and seas, those qualifications don't make the crossing. The language does, and the language implies more certainty than the instruments have yet provided. The rivers are worth looking at separately, because what researchers found when they tried to apply Earth's river equations to them is one of the strangest findings in planetary science of the last decade. When Huygens descended, the cameras captured image after image of the landscape below. There were channels, narrow drainage channels branching through brighter highland terrain, merging into wider valleys, running down toward darker lowland areas. The descent images showed what was unmistakably a river system, not a vague resemblance. An actual dendritic drainage pattern, tributaries feeding into trunk channels, the geometry of running liquid over time, carved into a landscape that had yielded to it. The ESA press release from January 2005 quoted Martin Tomasco, the principal investigator for the descent imager, geological evidence for precipitation, erosion, mechanical abrasion, and other fluvial activity, says that the physical processes shaping Titan are much the same as those shaping Earth. Much the same. But when researchers applied equations developed by Gary Parker equations calibrated against 491 rivers on Earth, and then tested against Martian paleoriverbeds, they found something unexpected. Titan's rivers, when the equations were applied, were predicted to move enough sediment to build deltas at their mouths. Deltas should be everywhere on Titan, at the edges of its seas. Fan-shaped deposits of sediment spreading out where rivers slow and drop their load. The way the Nile fans out into the Mediterranean, the way the Mississippi spreads across its delta, the way virtually every significant river on Earth deposits itself when it finally meets a body of standing water. On Titan, almost no deltas have been found. Cassini imaged the shores of the northern seas and lakes in radar pass after radar pass. 2 probable deltas, just 2, in the entire northern polar region, where hundreds of river systems drain into the seas. The proposed explanation is extraordinary. Titan's rivers may be denser than Titan's seas. When the river meets the sea, instead of slowing, spreading, and depositing its load at the margin, it plunges. It goes under. It carries its sediment down into the depths of the sea, depositing it in deep submarine fans that radar can't image through 100 meters of liquid. If this is right and it's a hypothesis, not a confirmed mechanism, then Titan's rivers behave like nothing on Earth. They arrive at the shore and disappear downward. The coastlines of Titan's seas are not where the rivers end. They're where the rivers go invisible. Think about what this means for the word shoreline. On Earth, a shoreline is a zone of deposition and erosion, of waves and deltas and gradual transition. It's the place where 2 things meet and negotiate. On Titan, a shoreline may be the place where a river vanishes without negotiation. The word shoreline arrived confident. But it may have brought the wrong geometry. Now the actual physics of the rain itself. Because the numbers here are where the analogy breaks most visibly and most concretely. A methane raindrop on Titan can grow to roughly 9 millimeters in diameter. On Earth, the maximum raindrop size before a drop becomes aerodynamically unstable and splits is around 6 millimeters. Titan's drops are larger because the atmosphere is denser and the gravity is weaker. Titan's gravity is about 1/7 of Earth's, somewhat weaker than the Moon's. The higher atmospheric density means more drag on a falling drop, which means the drop can grow larger before aerodynamic forces shatter it. A 9 millimeter raindrop in Titan's atmosphere falls at roughly 1 meter per second. On Earth, a raindrop falls at something like 9 meters per second. Titan's raindrops fall 9 times slower. This changes what rain does when it lands. On Earth, a raindrop hits the ground with enough kinetic energy to do work to detach soil particles, to kick up a splash, to begin erosion at the microscale. Cumulatively, across a year of rainfall, this impact erosion moves enormous quantities of sediment. It's a significant part of how rivers accumulate the material they eventually carry to deltas. Titan's methane drops hit the ground like slow drips. The erosive force is almost nothing. The kinetic energy of a Titan raindrop hitting the surface is roughly 1/80th of an equivalent drop on Earth. The sediment those drops can kick up and move is negligible. This feeds back into the delta problem. Titan's rivers seem to flow fast enough to carry sediment. The channel morphologies suggest significant flow velocities. But if rainfall impact is not a meaningful source of loose material, where is the sediment coming from? The pebbles in the Huygens landing images were rounded and sorted by transport, which means something moved them. The tholins accumulating on the surface are organic particles that settle from the atmosphere. The rivers seem to carry material, but the origin and quantity of that material are both uncertain. The water cycle metaphor suggests rain falls, erodes, feeds rivers. Rivers carry sediment to the sea. On Titan, the rain falls without meaningfully eroding. Rivers appear to carry sediment anyway by mechanisms that aren't fully resolved, and the sediment doesn't obviously arrive at the sea in the form of deltas. Every step in the analogy has a complication, not a refutation, a complication. The process happens, but not by the same mechanism. The result is similar, but through a path the analogy doesn't describe.
There's a name attached to the most influential early prediction about Titan's surface liquids. Jonathan Lunine, a planetary scientist who was, in the early 1980s, a graduate student working with the data from Voyager 1's 1980 flyby. Lunine was part of a group that modeled the fate of photochemically produced ethane on Titan's surface, and what they found was straightforward enough. If ethane had been accumulating since the solar system formed, it should have built up into a global ocean 1 to several kilometers deep, covering the entire surface.
A world entirely drowned in cold hydrocarbon fluid. The paper was published in 1983. The prediction was a global ethane ocean. When Cassini arrived in 2004, Titan had no global ethane ocean. It had lakes and seas at the poles, extensive, real, significant bodies of liquid, but it wasn't covered. The equator was a desert. The landscape was complex and varied, with dune fields and mountains and channels in various states of activity. The ocean Lunine and colleagues predicted wasn't there. In 1990, a ground-based radar experiment at the Arecibo Observatory bounced signals off Titan and found no evidence of a deep global ocean. The result was real but inconclusive, because shallow polar lakes would be consistent with it. Still, the global ocean prediction was quietly retired, and the model was updated to account for the fact that methane photodissociation produces more complex compounds than pure ethane, and that the cycle must involve ongoing replenishment. What Cassini did find, in the end, suggested that the early models were essentially correct in the physics and wrong in the geometry. Ethane was supposed to accumulate at the surface in large quantities, and it does mixed into the polar seas. Methane was supposed to cycle through the atmosphere, and it does. The prediction wasn't wrong, it was a different shape than expected. But notice what this history implies. The accepted account of Titan's methane cycle is not ancient wisdom. It's a framework that has been revised, tested, and updated over 4 decades of observation, against a single landed data point and the orbital returns of one spacecraft. The framework works, in the sense that it predicts things Cassini confirmed, but it was also capable of predicting a global ocean that didn't exist. The confidence in the current framework should be calibrated against that history. Carl Sagan and Stanley Dermott published a paper in 1982, the year before Lunine's ethane ocean prediction, calculating the tidal forces an ocean on Titan would exert on Saturn's orbit. The paper was titled "The Tide in the Seas of Titan." Sagan was imagining tides. A whole oceanography, Titan as a water world, except with hydrocarbons. Neither ocean nor tides were there. The scientists were not being sloppy. They were doing exactly what science requires, making testable predictions from the best available models. The models happened to have the geometry wrong, even when the physics was right. That is not a failure. That is how it works. But it is a reminder that the frameworks we use to describe Titan are younger than many of the people watching this. The whole vocabulary methane cycle, methane sea, methane rain, solidified only after Cassini arrived. In the years between 2004 and 2017, it is provisional in ways that the easy fluency of the language doesn't reveal. The methane source problem connects to something larger, and there's a specific number embedded in it that hasn't been looked at closely enough. The atmosphere will lose its methane in 10 to 30 million years at current destruction rates. That range comes from models of the photodissociation rate, which is well constrained by the solar flux at Saturn's distance and the known chemistry of methane under ultraviolet radiation. The uncertainty in the range comes from uncertainties in the escape rate of hydrogen, to space hydrogen being one of the byproducts of methane breakdown, and from uncertainties in how quickly the breakdown products are sequestered into surface deposits versus remaining in the atmosphere. 10 million years at the low end, 30 at the high end. The solar system is 4.5 billion years old. 10 million years is 1/450th of that. If Titan's methane is being continuously replenished from below from cryovolcanic outgassing of subsurface clathrate reservoirs, then the replenishment rate has to match the destruction rate, on average, over the timescale of Titan's history. That's a specific constraint. Something in Titan's interior has to have been producing and releasing methane at a rate that, integrated over billions of years, accounts for all the methane that's been destroyed. One alternative hypothesis, episodic rather than continuous, proposes that methane is released in massive pulses from subsurface clathrate reservoirs when those reservoirs are destabilized, perhaps by impacts or by changes in interior temperature or pressure. In this model, Titan's atmosphere is currently unusually rich in methane because we happen to be observing it shortly after a large pulse. In between pulses, the atmosphere would be methane poor. The clouds and rain and lakes would diminish or disappear, and Titan would look very different. If this is correct, then the Titan we observe, the Titan with rain and rivers and seas, is a temporary condition, not ancient, not permanent. A chapter, perhaps a brief one, in a history that includes long periods of a nearly dry, nearly cloud-free world. Papers dealing with Titan's long-term methane budget treat episodic release as a live possibility. The models that support continuous volcanic replenishment have not been confirmed by direct observation of active cryovolcanism. The candidate features are suggestive, but not definitive. The question of whether the weather Cassini observed is the weather Titan has always had, and will always have, that question is open. It might be seasonal weather in a much longer sense than we usually mean by the word season. This is a good place to examine the Northern Sea asymmetry, because its cause is one of the more unexpected findings in all of Titan science. The northern polar region has the great majority of Titan's surface liquid. The southern polar region has very little, a few lakes, including Ontario Lacus, the largest southern lake at about 15,000 square kilometers, and some putative Paleocea basins that are currently dry. The north-south asymmetry is stark. 12% of the area north of 55 degrees north latitude is covered by liquid, versus 0.3% in the equivalent southern region. The explanation that has gained the most traction is orbital mechanics. Saturn's orbit around the Sun is not a perfect circle. It is slightly eccentric, which means that Saturn's southern hemisphere summer currently occurs when Saturn is closer to the Sun, receiving roughly 25% more solar energy than the northern summer does. The south gets hotter summers. Hotter summers evaporate more liquid from the south and drive it via atmospheric circulation toward the north. Over tens of thousands of years, liquid migrates north. This is Titan's version of a Milankovitch cycle, the same type of orbital forcing that drives Earth's ice ages, operating through a completely different fluid, in a completely different direction. And here is what it implies. The liquid distribution on Titan right now is not in equilibrium. The north has accumulated liquid at the expense of the south, and this process is ongoing. Models suggest the dominant period for this north-south oscillation is around 45,000 years, driven by Saturn's orbital precession, but longer periods up to 270,000 years are also present, which means the southern polar region has Paleoceous dry basins that were once full, that held the equivalent of the northern Maria. and then were drained by the slow pull of orbital geometry. There are abandoned shorelines in the south, bathtub rings of evaporate deposits around Ontario Lacus, marking the edges of where the lake once stood. Incised channels suggesting a previous base level that no longer exists. Titan's coasts have moved, not in geological time, exactly in orbital time, in the time it takes Saturn's orbit to precess. And those coasts will move again as the orbital parameters shift back and the north begins its own long drying. The word coast on Titan comes with a 50,000-year uncertainty attached to it. The tholins deserve their own examination, because they are where the Earth analogy breaks hardest and strangest. Earth's water cycle is, at the chemical level, almost inert. Water evaporates, condenses, falls, runs off, soaks in. It dissolves things. It erodes things. But water itself does not chemically transform during this process in any significant way. The same water molecules that evaporate from the Pacific Ocean will eventually fall as rain and return to the ocean, essentially unchanged. Titan's methane cycle is not chemically inert. Every molecule of methane that reaches the upper atmosphere and is struck by ultraviolet light is changed. It breaks. The fragments recombine into new compounds: acetylene, ethylene, ethane, propane, benzene, hydrogen cyanide, and increasingly complex organic molecules that aggregate into the particles that make up Titan's orange haze. The haze is hundreds of kilometers thick. It gives Titan its distinctive color, the smoggy amber orange that Cassini photographed, the color that makes Titan look, from a distance, like a slightly clouded amber marble. These particles, called tholins, from the Greek word for muddy, settle out of the atmosphere over time. They fall onto the surface. They accumulate. The equatorial dunes are made largely of them. The riverbeds are filled with them. The dark material that colors the lowlands and gets washed down drainage channels is largely tholin organic sediment deposited from the atmosphere, and then reworked by the liquid methane that occasionally flows across it. The tholins contain complex organic molecules, including amino acid precursors, molecules that, on Earth, are considered part of the prebiotic chemistry, the chemistry that, given the right conditions, can lead toward the building blocks of life. These molecules are everywhere on Titan. They coat the surface. They mix with the methane rivers. They settle to the floor of the methane seas. In one reading, this is an enormous accumulation of chemistry. Titan's surface is, by some estimates, the largest known deposit of complex organic material in the solar system outside of the Earth. Not alive, but made of the kind of material that, on Earth, preceded life by somewhere between hundreds of millions and a few billion years. In another reading, it's inert. The temperatures are too cold for liquid water, which is the solvent that Earth's chemistry requires. The tholins sitting on the floor of Ligea Mare are in contact with liquid methane, not liquid water, and methane is not a chemistry-enabling solvent in the way water is, at least not for any life chemistry we understand. But that phrase, at least not for any life chemistry we understand, is doing real work. It is not a gesture toward speculation. It is an honest statement about the boundary of the question. What we understand about the chemistry of life is a sample of one. All the life we have ever examined derives from a single origin, uses the same genetic code, runs on water and carbon and the same 20 amino acids. We have exactly one data point for the chemistry that produces life. Titan has the carbon. It has the chemistry. It has a liquid fluid. It lacks water at the surface but has, according to evidence from Cassini's measurements of Titan's gravitational field, a subsurface liquid water ocean, probably at a depth of somewhere between 50 and 200 kilometers beneath the frozen crust, kept liquid by tidal heating from Saturn's gravity and insulated by the ice above it. Water, carbon, complex organics, liquid methane, and an energy source. This is not an argument that Titan has life. It is a list of the things that would have to be assembled before that question could even be asked properly. And the list is not short. Return now to the Magic Islands because they deserve more than a passing mention. Between 2006 and 2015, Cassini made multiple radar flybys of Ligea Mare. In one flyby in 2013, a bright feature appeared near the southeastern shore of the sea, a radar bright region, in a place that had shown no feature in earlier passes. In the next flyby, the feature had changed. In subsequent observations it changed again, sometimes appearing, sometimes not. The best explanations on offer are three: floating or suspended solids, bubbles rising from the lake bed, and surface waves disturbed by tides or wind. The researchers who analyzed the data couldn't exclude any of them and couldn't confirm any of them. Floating solids would require material less dense than the lake fluid possible if the solids were porous or if they were a particular composition, but the exact mechanism is unclear. Bubbles would require something generating gas at the lake floor, possibly the nitrogen exsolution process already described lake stratification, destabilizing and releasing dissolved gas in masses large enough for a radar instrument to detect from above. Surface waves is the most mundane explanation, and also the one with the most implications for exploration. Waves on Titan's seas would mean wind interaction with the liquid surface, which would mean the seas are actively exchanging momentum with the atmosphere, which would mean the fluid dynamics of the boundary layer above a hydrocarbon sea are operating in real time. The expected wave heights are tiny, a few centimeters, but radar at certain angles might enhance them into something detectable. The Magic Islands were never resolved. Cassini's mission ended in September 2017 when the spacecraft was deliberately commanded into Saturn's atmosphere to prevent it from potentially contaminating Titan or Enceladus with terrestrial microbes, and burned up. The islands were still unexplained when it died. There is a feature in a methane sea on a moon of Saturn that appears and disappears, and no one knows what it is. The word sea arrived there confident. It found this. The assumption that was accepted most easily, at the beginning, was this: that the similarities between Titan's cycle and Earth's water cycle are a framework, not a claim. That when scientists say methane rain, they know they're speaking metaphorically, and the metaphor is just shorthand. But shorthand does something to the questions it replaces. When you have shorthand for a process, you stop examining the process at the level of detail that generated the shorthand. The shorthand becomes the thing, and the thing the shorthand was standing in for all the specific, weird, non-analogous behavior of methane at 179 below that gets filed under basically like water, but cold, and questions that the water analogy can't generate because they require you to think about methane's specific chemistry. Rather than water's general behavior, those questions take longer to form. Here is a question that took a long time to form. Why don't Titan's rivers make deltas? On Earth, this would not be worth asking. Rivers make deltas. It's part of the cycle. You would not study delta formation on Earth looking for anomalies, because there aren't significant ones. On Earth, the river meets sea interaction is well understood. The river slows, drops its load. The delta forms. This is what rivers do. On Titan, the question was asked because someone applied Earth's river equations to Titan's rivers and found that Titan's rivers should be making deltas and weren't. The question arose from the failure of the analogy. The analogy had to fail before the question could be seen. If the analogy had been treated as identity, basically the same, the question might have been, where are Titan's deltas exactly, and what do they look like? Not, why is there no delta formation at all? The absence of deltas on Titan is, by current hypothesis, a window into the specific density relationship between Titan's rivers and Titan's seas, a relationship that has no terrestrial equivalent, that emerges specifically from the fact that the fluid is a methane-ethane-nitrogen mixture with a complex, temperature-dependent density profile that carries different sediment types at different densities than terrestrial rivers carry. None of that is visible through the water cycle frame. You have to leave the frame to see it. The frame was not wrong to use, but the frame had a cost, and the cost was exactly the places where Titan's behavior was most specifically alien, the places where the fact that this is methane, not water, mattered in a way the analogy couldn't accommodate. In the descent images Huygens sent back on January 14, 2005, there is one that is consistently reproduced in articles about Titan. It shows, from a few kilometers altitude, a branching network of dark channels cutting through brighter terrain, merging toward a darker plane at the bottom of the frame. It looks exactly like an aerial photograph of a river delta system somewhere warm and terrestrial, the kind of image you'd expect to see flying over the Niger Delta or the Lena River. The scientists who first saw that image, who spent years building the instruments that captured it, who had calculated for 20 years what Titan might look like, and then finally saw it, the response in the room was something specific. It was recognition. Not just confirmation of a model, something closer to the feeling of having arrived somewhere you've always known, or having seen a face you'd only imagined. That feeling was real. The similarity was real. The drainage patterns were real, and they were really formed by a liquid flowing downhill under gravity, exactly as rivers on Earth are formed. And the scientist at the controls, Martin Tomasco, who had spent his career building instruments to look at Titan, described it as extraordinarily Earth-like. It is Earth-like. That is not wrong. It is also, simultaneously, not Earth. The channels were carved by something falling from a cloud that has no equivalent on Earth. The liquid that carved them was at temperatures that would kill you in a second, in a way that burns would not, in a way that the word cold doesn't adequately describe. The bedrock the channels are cut into is ice. The sediment the channels carry is organic polymer material that doesn't exist on Earth's surface in any significant quantity. The rain that fed the channels may fall once every few centuries in any given location. The sea those channels drain toward is a body of fluid that can stratify into layers that don't mix, that can fizz with nitrogen from its floor, that has features that appear and vanish without explanation. The channels are real. The rivers are real. The seas are real. And the words are real too, but they arrived carrying cargo that doesn't fit, and some of that cargo is still being sorted out. In papers published this decade about rivers without deltas, and seas that fizz and rain that falls so slowly it feels like something other than weather. The timescale problem. The rain stops and doesn't come back for a century. That's where the first pressure left the ground at the question of what kind of thing Titan's weather actually is, if it isn't weather in the sense that word carries. A century between rainfalls at any given point. Polar lakes filling over tens of thousands of years in response to orbital forcing. Methane that is being photochemically destroyed and may be volcanically replenished from reservoirs that formed when the solar system was young. A cycle, if you want to call it that, which might be less like a water cycle and more like a breathing pattern, long, slow inhales and exhales driven by processes that operate over timescales no human institution has ever had to think about. On Earth, the word weather means something that happens continuously and relatively quickly. Rain falls this week or last week. A storm system passes in hours or days. The weather you experienced yesterday is recognizably the same kind of thing as the weather you'll experience next month, even if the specific conditions differ. Weather is a process running in human time, not in geological time. not in orbital time. Climate is slower. Climate is the statistical envelope that weather occupies over decades. And then beneath climate is geology, the reshaping of landscapes over millions of years. These categories are distinct on Earth because the timescales are distinct. A rainstorm is weather. The carving of the Grand Canyon is geology. The categories don't overlap. On Titan, they might. The methane cycle operates simultaneously on at least 3 timescales that on Earth would belong to completely separate categories of process. The first is the fast one-storm events, seasonal cloud formation, rainfall during convective outbursts. These operate on the timescale of Titan's year, roughly 30 Earth years, and within that year on the timescale of months. The equatorial storm of 2010 produced dark, wet surface marks that dried over subsequent months. This is weather, in the sense that Earth uses the word. The second is the orbital one, the slow migration of liquid from south to north and back again, driven by the eccentricity of Saturn's orbit. This takes 45,000 years for a full oscillation. The southern Paleoceas, currently dry, were full within the last 100,000 years or so. The shorelines of the northern Maria are still rising slowly as liquid accumulates from ongoing south to north transport. This is not weather. On Earth, this would be called climate or perhaps Milankovitch scale glaciology. But on Titan, this process directly controls whether it rains at a given latitude, how much evaporation occurs, where the vapor goes, where the clouds form. It is inseparable from the weather. The third is the geological one, the methane replenishment timescale. If cryovolcanism is the source, then the methane in today's atmosphere may have been stored in the crust for hundreds of millions of years before being released. The rain that is falling on Titan right now may be falling with molecules that were locked in a water ice cage beneath the surface since before the dinosaurs existed. And the rain that will fall in 100 million years, if the supply holds, will depend entirely on whether Titan's interior is still warm enough to drive the volcanic activity that releases it. That third timescale is not weather, it's not climate. It might not even be geology in the usual sense. It's planetary chemistry, the slow transaction between a moon's interior and its atmosphere, mediated by cryovolcanism that we haven't definitively confirmed and can only infer. All 3 timescales are part of the same cycle. They are not separable. The methane that evaporates from Ligeia Mare this Titan summer was delivered to the atmosphere by processes operating on all 3 scales simultaneously. There is no word for that. Water on Earth goes through its cycle on one dominant timescale. The atmospheric residence time of a water molecule is roughly 10 days before it falls as rain. The deep water cycle, water subducted into the mantle and returned via volcanism, operates on geological timescales. But it is so slow and volumetrically small compared to the fast cycle that it barely registers in the water cycle as most people understand it. The 2 timescales are decoupled. The fast one is weather. The slow one is background geology. On Titan, the 2 timescales are coupled. The fast cycle, methane, rain and evaporation and cloud formation, is dependent on the slow cycle for its raw material. Without cryovolcanism, or without whatever mechanism is replenishing the methane, the fast cycle runs down. The rain stops, not for a century, forever, or until the next geological pulse. The accepted account says methane cycle, and implies something self-sustaining, the way Earth's water cycle is self-sustaining. But Earth's water cycle is self-sustaining. Because it is essentially closed, the water is not being consumed, just moved around. Titan's methane is being consumed. Something external to the fast cycle has to keep feeding it. Every drop that falls was purchased against a reservoir whose balance and source are both uncertain. The seas on their own terms. A sea on Earth is fundamentally a solution. It's mostly water, with salts and dissolved gases and organic material and microorganisms. It has a chemistry, but it's a chemistry that operates around the central fact of liquid water, a polar solvent, meaning one that dissolves ionic compounds easily, that can form hydrogen bonds, that can support the molecular interactions that living things depend on. The seas of Titan are not solutions in this sense. They are mixtures of two non-polar organic solvents, methane and ethane, with dissolved nitrogen and trace quantities of other compounds. The chemistry they can support is fundamentally different from the chemistry water can support. Non-polar solvents are not inert, they dissolve non-polar compounds, including many complex organics. The tholins that rain down onto Titan's surface from the atmospheric haze contain some fraction of material that would dissolve in the methane-ethane mixture of the seas. What fraction and what happens to those compounds once they're in solution? Those are questions significantly harder to study from orbit than the question of how deep the seas are. The composition of the seas has been partially constrained. Ligea Mare was probed by Cassini's radar altimeter in a way that measured not just depth, but the attenuation of the radar signal passing through the liquid, and the attenuation was very low, remarkably low, lower than any known liquid on Earth. A loss tangent around 4 × 10⁻⁵. What this means physically, the liquid in Ligea Mare is almost perfectly transparent to microwave radiation. There are essentially no ions, no suspended particles, no dissolved polar compounds to absorb or scatter the radar. The sea is extraordinarily clean in the sense of being a pure mixture, close to pure methane and ethane and nitrogen, without the complex chemistry that would make it absorb radar. The same radar measurement that let researchers calculate the depth of Ligea Mare also, in its very precision, revealed how simple the sea is. Not sterile simplicity and sterility are different things, but chemically simple in a way that Earth's oceans are not and have never been. On Earth, the ocean is where chemistry happens. It's a reactor. From the earliest oceans of the Hadean to the present, the ocean has been a place where molecules meet and react, where gradients between hot and cold, between oxidized and reduced, between concentrated and dilute, drive chemistry forward. The ocean's complexity, its ionic strength, its buffering capacity, its dissolved organic carbon, is inseparable from its role in Earth's chemistry of life. Titan's seas may be too clean for that. A sea that is essentially pure methane and ethane is a sea in which almost nothing dissolves, in which almost nothing reacts, in which the liquid is a transport medium rather than a reaction chamber. The tholins that wash into the sea from the rivers, the small quantities of dissolved organics, these exist at concentrations so low that meaningful chemistry between them would require timescales that are hard to estimate and conditions that are hard to specify. This does not mean nothing interesting is happening in Titan's seas. It means the interesting chemistry, if any, is happening in the thin interface zones, the shores, the river mouths, the floors where sediment accumulates, the places where concentration gradients exist. The interior of a clean methane-ethane sea may simply be a cold, transparent, slow-moving body of fluid that moves methane from where it evaporated to where it will eventually evaporate again. Vast, cold, clean, and in its interior essentially inert. The shoreline AS timeline. The shorelines of Titan's northern Maria show something that the word shore doesn't adequately capture. Ligea Mare has a shoreline that is deeply crenulated, jagged, complex, full of bays and peninsulas and drowned river valleys where the rising liquid level has flooded terrain that was previously above the waterline. The sea is not in a stable edged basin. It is actively encroaching on the landscape around it. The drowned river valleys are the clearest evidence of this. They look, in the radar images, like estuaries, places where a river valley that once drained toward a lower base level has been inundated by rising fluid. The sea came up. The valley floor that once carried flowing liquid now holds standing liquid. The transition from river to sea has been erased by the sea's advance. This has happened on Earth. 2 sea level rise after glacial melting flooded river valleys, creating estuaries and fjords. On Earth, that flooding was driven by climate ice ages ending, temperatures rising, ice melting, ocean volume increasing. The timescale was thousands of years, and the cause was a climate shift. On Titan, the flooding of Ligeia Mare's river valleys is being driven directly by orbital mechanics, by the slow, steady northward transport of liquid from the south over tens of thousands of years, as Saturn's orbital eccentricity tips the volatile balance toward the North Pole. On Earth, orbital mechanics affects climate, which affects ice, which affects sea level, a long chain of mediated effects. On Titan, the chain is shorter. Orbital mechanics directly controls where the methane is, and the methane's location is the coastline. The shorelines of Titan are where orbital mechanics and chemistry and weather intersect in a single visible line. That line is moving, and it will reverse, and it has reversed before, and there is no human institution old enough to have observed it reverse once. Near the shores of the northern Maria, what appear to be ancient shorelines, exist elevated flat surfaces, evaporate deposits at higher elevations, marking where the sea stood during a previous orbital cycle, before the liquid drained away to the south. If you could stand at the current shore of Ligeia Mare and look inland, you would be looking at the floor of an old sea. The beach you're standing on is new. The landscape around you is the memory of a previous sea. The word shore arrived with the present tense. What the shore actually is a timeline. What the evaporites remember. Evaporites are deposits left behind when a liquid evaporates and the dissolved material it carried precipitates out. On Earth, the great evaporite deposits, salt flats, gypsum beds, limestone formations are archives of ancient seas.
They record what was dissolved in the water, and therefore something about the water's history, the climate that dried it up, the chemistry of the ocean it came from. On Titan, evaporite deposits appear as bright features in the infrared data, bright at 5 micrometers wavelength, a spectral signature that doesn't match any obvious material but is interpreted as an organic compound, perhaps acetylene or some more complex molecule from the tholin family, concentrated and deposited as the lake or sea that carried it evaporated.
These 5 micrometer bright deposits appear not just at the edges of existing lakes, but across much larger areas, including features near the equator, in Haute Regio and Tui Regio, that may be the remnants of ancient low-latitude seas that dried up long before Cassini arrived. If this interpretation is right, then Titan's equatorial desert, the arid region of dunes and channels, was once covered, in places, by liquid seas. The dunes that now sit there may be built on the evaporite beds of those ancient seas, which would mean the organic material in the dunes is partly recycled from ancient lakes, transported by wind after the liquid was gone. The equatorial dune material and the polar sea composition and the ancient evaporites may all be connected different phases of the same material, moved between states and locations by the slow orbital oscillation of Titan's liquid inventory. The desert and the sea are not opposites on Titan. They may be the same material in different stages of a cycle that takes hundreds of thousands of years to complete. There is no vocabulary for that either. Desert and sea on Earth are separated by categories, climate zones, geology, biology. On Titan, they may be the same place at different times. The dunes that point the wrong way. The equatorial dunes of Titan are visible in Cassini's radar images as long, parallel, slightly sinuous ridges running roughly east-west across the equatorial region, extending for hundreds and sometimes thousands of kilometers. They're longitudinal dunes, a shape that on Earth forms when winds blow in 2 directions that aren't exactly opposite. producing a net drift in the direction of their vector sum. They imply a prevailing wind pattern, a consistent circulation, an aeolian regime operating over the timescale needed to build dunes hundreds of meters tall. The dune sand is dark. Dark in the radar, dark at infrared wavelengths. The color and radar behavior are consistent with complex organic material, the tholins and other photochemical products raining down from the atmosphere. There is enough of this material to build dunes across the entire equatorial belt of a world roughly 40% the size of Earth. By some estimates, the organic material in Titan's equatorial dunes contains more carbon than all of Earth's known coal reserves. Those dunes are being shaped by wind, and here the accepted account encounters a strange problem. The dunes are oriented such that they imply the dominant winds blow from west to east. But models of Titan's atmospheric circulation, based on the temperature structure and the Huygens wind measurements during descent, predict winds that should blow from east to west, at the surface near the equator, the direction you'd expect from the same kind of temperature gradient that drives trade winds on Earth. The dunes are pointing the wrong way. Several explanations have been offered. One is that the near-surface winds reverse during equinoctial storms, the rare large events like the 2010 outburst, and that these brief reversals, even if they happen only once every Titan year or less, are the episodic events that actually move the dune sand. The gentle prevailing wind blows in the expected direction and does nothing to the sand. The rare, powerful equinoctial wind blows the other way and moves everything. In this model, the dunes on Titan are built primarily by rare catastrophic events, not by the slow, persistent wind that blows most of the time. This changes the character of what you're looking at. If the Titan dunes were built by ordinary weather, by the trade wind equivalent, blowing steadily for years, they would be an archive of the typical. They'd record the average. But if they're built by exceptional events, they record the catastrophic. The landscape is shaped not by the everyday rain and wind, but by the storm that comes once a Titan year, or once every several years, and moves everything. A landscape shaped by a 30-year storm, happening reliably, predictably, every time the sun crosses Titan's equator. The man who built the camera. There is a person in this story who is not famous outside of planetary science, and whose specific moment belongs here in a way that other tellings of Titan's history tend to move past quickly. His name was Martin Tomasco. Martin G. Tomasco was a planetary scientist at the University of Arizona's Lunar and Planetary Laboratory. He spent 22 years building the Descent Imager's spectral radiometer, the DESIR, the instrument on Huygens that captured the images of the channels and the pebbles and the haze structure of Titan's atmosphere during the descent. 22 years. He started working on the instrument in 1983, when Lunin and colleagues had just published their ethane ocean prediction. He spent 2 decades designing a camera to photograph something that, at the time, might have been an entirely liquid world, something that might look like a featureless expanse of liquid hydrocarbon under an orange sky with no solid surface to image. The Huygens probe was released from Cassini on December 25, 2004. It coasted toward Titan for 3 weeks. On January 14, 2005, it hit the atmosphere at 21,000 kilometers per hour, decelerated to 140 meters per second in about 4 minutes, then opened its parachutes and began the slow descent. Tomasco was in the control room in Darmstadt, Germany, the ESA facility that was receiving and processing the data. The images from DESIR were coming in as the probe descended. The first images showed haze, then the top of the clouds. Then, as the probe dropped below the main cloud deck, the surface began to resolve, and there were channels. And there were the merger points where channels became valleys. and there was the darker plain at the bottom of the valley. He had built a camera to image a possible liquid world. He was imaging a possible fluvial one instead. The world underneath the orange haze was not an ocean. It was a landscape. It had highlands and drainage and a flat, dark plain that might be a dry lake bed or might be a damp, dark sediment surface, or might be something else entirely. He told the press, "We now have the key to understanding what shapes Titan's landscape. Geological evidence for precipitation, erosion, mechanical abrasion, and other fluvial activity says that the physical processes shaping Titan are much the same as those shaping Earth. Much the same." He was right about the processes. He was reaching for language, and the language he had was Earth's, because there wasn't any other. The Earth vocabulary was the only one available in that room, in that moment, with those images arriving. Tomasco died in December 2015, 10 years after the descent. He spent his last years continuing to analyze the DISAR data, the paper that extracted the methane humidity profile from the descent data, the detailed characterization of how methane varied with altitude throughout the atmosphere, came out after he died. His instrument, and what it found, remain the only direct visual record of Titan's surface and lower atmosphere from below the clouds. Everything after him has been inference from orbit. He saw it once, for 72 minutes, and the vocabulary he reached for was the only one the human species had. It is not a criticism of Tomasco to say that the vocabulary he used carried more certainty than the measurement justified. In the moment, images arriving from 1.25 billion kilometers away, from the first landing in the outer solar system, from a world no one had ever been closer to than a spacecraft moving at 5 kilometers per second in that moment, reaching for the closest available language was not a failure. It was the only possible move. The science would refine the language. That is how science works. But the refinement takes time, and in the meantime the language runs ahead of the data. It runs especially far ahead in the popular account, the one that says Titan is Earth-like, that it has weather like ours, that it's a world that mirrors Earth in some essential way. That account is not wrong, but it is faster than its evidence, and the places where it's fastest are the places where Titan is most specifically itself. The channels that Tomasco's camera imaged are real. The pebbles on the floor of the riverbed are real, rounded by transport in a liquid, shaped by the same physics that rounds pebbles on Earth. The process is the same. The physics is the same. Gravity, flowing liquid, mechanical abrasion. The liquid was at -179 degrees Celsius. The pebbles were water ice. The sediment coating the floor was a complex polymer produced by photochemical reactions in an atmosphere of nitrogen and methane and the products of their breakdown. The rain that fed the rivers falls, at that location, less often than a human lifetime. The process is the same. The substance is not. And the substance matters. It matters in ways that the process-level analogy conceals. And those concealed places are where the most interesting questions currently live. What the lakes ate. Titan's lakes, not the large Maria, but the hundreds of smaller lakes in the northern polar region, include many that have sharp edges and flat floors and no visible inlet or outlet channels at the resolution of the Cassini radar. These are the sharp-edged depressions, lakes that sit in topographic basins that appear to have formed by a process other than fluvial erosion. No river carved them. They are simply depressions in the landscape, sometimes hundreds of meters deep, with edges so sharp they look punched rather than carved. The proposed mechanism is dissolution, the same process that creates karst landscapes on Earth, where groundwater dissolves soluble rock and the surface above collapses into the resulting cavity. On Earth, this happens in limestone terrain, where calcium carbonate dissolves in slightly acidic groundwater. The result is sinkholes, caves, and the characteristic dimpled landscape of karst. On Titan, the soluble material is not limestone. Water ice, the bedrock of Titan, is essentially insoluble in liquid hydrocarbons. The material that can dissolve in methane and ethane is organic material, the tholins, and simpler organic compounds that have been accumulating at the surface for billions of years. If thick deposits of soluble organic material underlie parts of Titan's polar terrain, then liquid methane seeping into the subsurface could dissolve it, leaving cavities that eventually collapse into the surface lakes. This would make some of Titan's lakes not lakes in the usual sense, not basins carved by rivers and filled by rain, but dissolution features. Titan sinkholes. The surface is eating itself from below, as methane percolating downward dissolves the organic rich layers and removes the material that used to be there, leaving voids that collapse and fill. Some of Titan's lakes may not have inlet channels because the liquid didn't arrive at the surface. It came from below. The lake is where the ground fell in, and the methane rose up to fill the space. A lake that appeared from below, in a hole the ground made by consuming itself. The word lake arrived assuming a surface process the basin formed. The rain filled it. The shoreline defined it. On Titan, some lakes may be the surface registering what's happening underground. Cavities forming in organic sediment. The landscape losing material it can't replace, collapsing inward, and the resulting hole filling with liquid that came up through the same porosity that caused the collapse. The lake is where the land used to be. The methane table. This connects to something the accepted account mentions briefly and then moves past. Titan may have a global subsurface methane table. The Cassini-IS and VIMS instruments tracked Titan's clouds for 13 years. And the cloud patterns that emerged didn't match any of the atmospheric models that assumed the only methane sources were the visible lakes and seas. The models that came closest to matching the observed cloud distributions, specifically the timing and location of cloud formation at mid-northern latitudes, earlier than expected, and the persistence of cloud activity in both polar regions, were models that included a widespread subsurface methane reservoir extending beyond the visible lakes, like a water table, accessible to the atmosphere through evaporation and seepage. A methane water table. Not under the ice crust, not the deep subsurface ocean of liquid water that sits tens of kilometers down. At or near the surface, a porous, wet layer of hydrocarbon-saturated soil and rock extending across the polar regions, feeding the atmosphere with methane vapor, the way a wet soil feeds a terrestrial atmosphere, by slow evaporation from millions of small pores rather than from visible surface liquid. If the subsurface methane table is real, then the amount of liquid methane on Titan is significantly larger than what's visible on the surface. The visible lakes and seas are the top of a saturated zone, the way a lake or pond is the visible expression of a local water table. Below the surface, filling the pore spaces of the substrate for hundreds of meters or kilometers, there may be methane that has never appeared at the surface, that has never been rained and never evaporated, that simply sits in the cold, dark, porous rock and ice, seeping slowly toward any available outlet. The amount of methane implied by this, if the models are right, is large enough that the methane budget comes closer to closing. A large subsurface reservoir could be the bridge between the visible surface liquid and the atmospheric methane supply. It could explain how the atmosphere stays supplied even during the long northern winter when evaporation from the polar seas is limited. It could explain why the clouds form when and where the models need them to. But it hasn't been measured. The subsurface methane table is inferred from cloud behavior, not detected directly. There are no boreholes on Titan. There is no seismic network. There is no instrument yet flown that can measure what's in the pore spaces of the polar substrate. It is a real inference from real data, carefully made. And it is possible, likely, perhaps, and completely unconfirmed. What all of these things add up to the three timescales: the clean seas, the dissolving lakes, the dune sand blown by catastrophic winds. The subsurface methane table is something the water cycle frame can't hold in one frame. On Earth, the liquid, the atmosphere, the solid surface, and the subsurface are relatively separate systems. The atmosphere is mostly gas. The surface is mostly solid. The ocean is liquid. The transitions between them are slow and mediated. The ocean doesn't easily become atmosphere. The bedrock doesn't dissolve into the ocean. The subsurface doesn't routinely communicate with the surface weather. On Titan, all of these boundaries are more permeable. The atmosphere exchanges methane directly with the subsurface table. The surface organic material dissolves into the liquid and forms lakes. The lake floors may exchange nitrogen with the atmosphere through bubble formation. The liquid moves from pole to pole over orbital timescales. The dune sand solid material was once atmospheric haze and will perhaps one day be seafloor sediment. The methane that rains down was once gas, and before that was locked in ice, and before that may have been in the interior for billions of years. Everything on Titan is in more conversation with everything else than it is on Earth. The categories weather, geology, chemistry, oceanography don't hold their Earth-shaped boundaries. The water cycle frame was borrowed from a world in which those boundaries hold. Applied to Titan, it describes the surface correctly and misses the depth. Not because the scientists using it are wrong, but because the frame was built for a world where depth and surface are more separate than they are here. The word that hadn't appeared yet. There's a word that hasn't appeared yet in this inquiry, and its absence has been its own kind of finding. The word is prebiotic. Not because it's the right conclusion, it isn't a conclusion, and this script doesn't arrive at conclusions it hasn't earned, but because the word is used freely in the scientific literature, in the mission objectives for Dragonfly, in the papers about tholins and organic chemistry, and its presence there raises a question the inquiry has been circling without naming directly. Prebiotic means before life. It means the chemistry that came before biology, the chemistry that on Earth preceded the first cells. Amino acid precursors, nucleotide precursors. The molecules that, given the right conditions, given time and energy and the right solvent, began to organize into the larger structures that eventually became self-replicating and eventually became alive. That chemistry exists on Titan, not in trace quantities. In quantities that dwarf anything on Earth. The tholins alone, the organic haze particles that fall continuously from the atmosphere and coat every surface and fill the dune fields and settle to the floors of the seas, represent an accumulation that has been ongoing for possibly the entire age of the solar system. 4.5 billion years of prebiotic chemistry, falling like snow. On Earth, the prebiotic period lasted somewhere between a few 100 million years and perhaps 1 billion years, the window between when the planet cooled enough to have liquid water and when the first evidence of life appears in the fossil record. During that window, the chemistry ran. The molecules assembled. The conditions were met. We don't know exactly how long it took. We don't know exactly what conditions were required. The origin of life is one of the most studied and least resolved questions in science, and the reason it's least resolved is that the event happened once, left no direct record, and occurred under conditions we can only reconstruct indirectly from what came after. What we do know is that it required certain things: a solvent capable of supporting molecular interactions, energy gradients to drive chemistry forward, a supply of the right molecular building blocks, and time. Enough time for rare events to occur and be preserved and compounded. On Earth, the solvent was water. The energy came from hydrothermal vents, lightning, ultraviolet radiation. The building blocks included molecules like those found in Titan's tholins. The time was measured in hundreds of millions of years. On Titan, the building blocks have been accumulating for 4.5 billion years. The energy sources include tidal heating from Saturn and ultraviolet radiation from the Sun. There is no liquid water at the surface. There is liquid methane and ethane at the surface. And there is, deep beneath the surface, liquid water kept liquid by tidal heating, insulated by 100 kilometers or more of ice. Two separate chemical environments, one cold and hydrocarbon rich, one warm and water rich, separated by a thick layer of ice that might, in places, be porous enough to allow slow exchange. What kinetics doesn't settle. The temperature argument runs deepest through the accepted account, and it deserves to be looked at more carefully than it usually is. Negative 179 degrees Celsius is very cold. Chemistry slows dramatically at low temperatures. Chemical reactions that proceed in seconds at room temperature might take millions of years at Titan's surface conditions. This is the principal reason that life as we understand it cannot exist at Titan's surface. The kinetics are too slow. But kinetics is not the only relevant consideration. Thermodynamics is the other one. Thermodynamics asks whether a reaction is favorable, whether the products have lower energy than the reactants, whether the process releases or requires energy. A reaction that is thermodynamically favorable but kinetically slow will still proceed, given enough time. It will just proceed very slowly. 4.5 billion years is a great deal of time. This is not an argument that Titan has life. It is a statement about the limits of the kinetics argument. Slow chemistry running for a very long time is not the same as no chemistry. The question of what 4.5 billion years of slow prebiotic chemistry on a hydrocarbon-covered surface has actually produced is not answered by pointing to the temperature. It is answered by measuring the surface, which has not been done in any comprehensive way. There is, in the astrobiology literature, a concept called the cold start hypothesis for Titan, the idea that if any biochemistry were to emerge on Titan, it would be fundamentally different from Earth biochemistry, using liquid methane or ethane as a solvent instead of water, using different molecular scaffolding, running at temperatures where Earth biochemistry would be frozen solid. This has been modeled theoretically. The molecules that could form cell membrane analogues in a methane solvent have been proposed they would need to be fundamentally different from the phospholipid bilayers that Earth's cell membranes are made of. But the thermodynamics of forming closed vesicles in a non-polar solvent has been worked out, at least on paper. This is not science fiction. It is published, peer-reviewed theoretical chemistry. It is speculative in the sense that it has no observational support. There are no detected structures on Titan consistent with methane-based membranes, and no known organism that uses a non-polar solvent. But the fact that it has been worked out theoretically means the question can at least be asked. Whether life is possible in liquid methane is no longer simply answered by "of course not." The temperature is wrong. The temperature is wrong for Earth life. Whether it is wrong for some other kind of chemistry that we haven't observed, that is the question that Dragonfly will begin, at the edges, to press on. The vinyl cyanide detection. There is a specific detection that made the cold start hypothesis suddenly more concrete, and it deserves to be the anchor here rather than the theory that surrounds it. In 2017, researchers reanalyzing data from the Atacama Large Millimeter Array confirmed the presence of acrylonitrile, also known as vinyl cyanide, in Titan's atmosphere. Vinyl cyanide is a molecule that, at Titan's surface temperatures, can spontaneously form closed membrane-like structures in liquid methane. Not identical to cell membranes, very different from cell membranes, but structures that share the essential property of forming a boundary between inside and outside, which is one of the things a cell membrane is for. The concentrations detected were small. The detection was real. Vinyl cyanide exists in Titan's atmosphere in quantities that, if it were dissolving into the polar seas at a comparable rate, could produce on the order of 10 million of these membrane-like structures per cubic centimeter of liquid, roughly comparable to the density of bacterial cells in Earth's surface ocean. That number is not evidence of life. It is a statement about potential. The membrane-like structures that vinyl cyanide can form have not been detected in Titan's seas. The chemistry that would need to occur inside a vinyl cyanide vesicle, the equivalent of the internal chemistry of a cell, has not been proposed in any detail. The analogy to bacterial density is not an argument that bacteria exist. It is a way of saying that the raw material for boundaries exists in sufficient quantity to be interesting. Still, it is interesting. And it is the kind of finding that the weather frame does not naturally generate. If you are looking at Titan as a world with weather, you are looking at the methane cycle, the cloud patterns, the precipitation rates. Vinyl cyanide in the atmosphere is a footnote, an interesting atmospheric chemistry detail. If you are looking at Titan as a 4.5 billion year chemistry experiment, vinyl cyanide in the atmosphere is a potentially central finding. The frame you use determines what you see as central and what you see as peripheral. That is the cost of frames. They organize. And what they organize toward, they see. What they organize away from, they note in passing. The ocean below the ice. Cassini measured Titan's gravitational field with extraordinary precision, tracking tiny changes in the spacecraft's velocity as it flew past the moon. What it found in the gravity data was that Titan flexes. The shape of the moon changes slightly as it orbits Saturn, deformed by Saturn's tidal pull. The amount of flexing is called the tidal love number, and its value constrains the interior structure of the moon. Titan's tidal love number was measured at roughly 0.6. A rigid ice body at the same size and composition would have a love number around 0.13. The discrepancy means Titan's interior is not rigid. There is something fluid inside that allows the tidal deformation to be amplified. The most straightforward interpretation is a subsurface liquid water ocean lying beneath the outer ice shell, at a depth that recent models put at somewhere between 50 and a few hundred kilometers. The ocean would be kept liquid by the combination of tidal heating, the friction of Saturn's gravitational kneading, and residual radiogenic heat from the decay of radioactive elements in the rocky core. The water in this ocean would not be pure. At those temperatures and pressures, it would likely contain dissolved ammonia, a natural antifreeze that lowers the melting point and keeps the water liquid at temperatures well below 0 Celsius. Ammonia water has been proposed as the working fluid in cryovolcanism, the slurry that rises through the ice and delivers methane to the surface. This ocean has not been directly detected. The gravitational inference is strong enough that most planetary scientists treat Titan's subsurface ocean as likely, probably certain. But the same was said of Europa before the first direct evidence of its ocean plumes emerged. And even there, the subsurface was only confirmed as a probable ocean from gravity and magnetic data, not from direct sampling. What would it mean if Titan has a liquid water ocean that has been sitting beneath its ice crust for billions of years? It would mean that on Titan there are two liquid environments simultaneously: a cold hydrocarbon surface built of methane and ethane, a deep water ocean, potentially with dissolved salts and ammonia, heated from below, isolated from the surface by a thick ice barrier, each environment carrying, in principle, different chemistry. Each environment separated from the other by a distance measured in tens of kilometers. The question of whether any chemistry in the deep ocean has ever come in contact with the chemistry at the surface is the question of whether the ice barrier is truly sealed. If Titan has cryovolcanism, if there are vents through the ice, through which the water ammonia fluid rises, then there are places where deep ocean chemistry and surface chemistry meet. On Earth, hydrothermal vents on the ocean floor are places where heated water rises through rock, dissolving minerals and delivering them to the cold deep ocean, a chemistry gradient that may have been the cradle of life on Earth. The energy gradient between hot vent fluid and cold surrounding ocean drives the formation of complex molecules. Life at hydrothermal vents on Earth is extraordinarily diverse. On Titan, if there are cryovolcanic vents, the gradient would be inverted in its geometry but analogous in its principle. Warm water rising through cold ice, emerging into an even colder hydrocarbon surface, delivering chemistry from one environment to the other. The meeting of liquid water and liquid methane at a cryovolcanic vent on Titan, if such a thing exists, would be a chemistry event unlike anything that has ever been observed by anyone, anywhere. No one has observed it. No instrument has been close enough to detect it. The evidence for cryovolcanism remains indirect and contested. But the possibility is consistent with everything that is known about Titan's interior. And three independent lines of evidence, the gravitational love number, the argon-40 in the atmosphere, and the unaccounted methane, all point toward an active interior, without any one of them constituting direct proof. What frames cost? The inquiry needs to say something directly about what the dominance of the weather frame actually cost, beyond the general observation that frames have costs. It cost specifically 20 years. From the Huygens landing in 2005 to the approval and design of Dragonfly, which was selected for funding in 2019 and confirmed in the mid-2020s, the primary scientific frame for Titan was meteorological and geological. How does the methane cycle work? What are the cloud dynamics? How much rain falls? What shaped the dunes and the rivers and the channels? These are good questions and they produced good science. But the chemistry question, what has the weather been making? What has accumulated in 4.5 billion years of tholin deposition? What does the surface organic inventory actually consist of? That question was being asked by astrobiologists and organic chemists throughout that period, in papers that cited the same Cassini data through a different frame, and it did not drive a mission until Dragonfly. The shift that produced Dragonfly was not better data. It was a different question being asked of the same data, not what is the weather doing, but what has the weather been making. Those two questions are not opposites. They are the same process seen at different timescales. The weather, in real time, carries tholins from the atmosphere to the surface. It rains methane over the dune fields, washes the tholins into drainage channels, carries them toward the polar seas, deposits them in the seafloor sediment. This is weather as a delivery mechanism for chemistry. Over geological time, the weather is an organic chemistry engine. It takes nitrogen and methane from the reservoir, runs them through the photochemistry of the upper atmosphere, produces complex molecules, delivers them to the surface, concentrates them in certain locations, and leaves them there. The weather is making the chemistry that the chemistry question is asking about. What the water cycle frame misses is not that the chemistry exists, it doesn't deny the chemistry exists. What it misses is that the chemistry is the point. The rain is not just precipitation. It is a delivery system for the raw material of everything that makes Titan interesting. On Earth, rain delivers water, and water is the solvent that life needs. And so rain is indirectly connected to life, but not in any direct sense doing chemistry. On Earth, the water cycle and the carbon cycle are separate. The rain falls. Separately, the carbon compounds cycle through atmosphere, ocean, and biosphere. On Titan, the rain and the carbon are the same thing. The methane that rains is a carbon compound. The sediment the rain washes is a carbon compound. The haze that settles is a carbon compound. The bedrock is water ice, and the water ice is the geologically inert substrate that the carbon chemistry operates on top of. Rain on Titan is the carbon cycle. The weather and the chemistry are not separate systems, they are a single process. And so when you use the word rain and mean only precipitation, only the meteorological fact of liquid falling from a cloud, you have named the delivery, but not what is being delivered, and not what happens to what is delivered, and not what that delivery has been accumulating into for 4.5 billion years. The word carries the physics. It does not carry the chemistry. The complexity question. There is a sentence worth testing. Titan is the most complex world in the solar system that is not Earth, not to argue for it, to find where it breaks. Mars has been more extensively studied. It has been landed on repeatedly, driven across by rovers, analyzed in situ. Its chemistry is better characterized at the surface than Titan's is. But Mars is a dead world in the relevant sense. Its atmosphere is thin and cold and nearly inert. Its surface frozen and radiation blasted. Its interior largely cold and geologically quiet. The chemistry on Mars is the chemistry of oxidation and mineral precipitation, essentially the same chemistry as terrestrial desert geochemistry, but in a harsher version. Europa has a subsurface ocean. Its ice surface shows evidence of ongoing geological activity. The ice is young, constantly resurfaced, cracked by tidal forces. But the surface is almost entirely water ice and radiation-processed organics, and it has no atmospheric chemistry. No rain, no rivers, nothing at the surface doing chemistry in real time. Enceladus has active plumes of liquid water erupting from its south pole. It is the most actively confirming candidate for an extraterrestrial ocean. But Enceladus is small, it has no atmosphere, no surface geology beyond what the plumes create. And the chemistry accessible to observation is limited to what Cassini flew through in the plume. Titan has a thick atmosphere actively producing complex organic chemistry, a surface covered in that chemistry and reworked by liquid processes. A liquid hydrocarbon surface layer in real-time meteorological exchange with the atmosphere, a subsurface methane table in exchange with the atmosphere, a deep water ocean possibly in exchange with the surface via cryovolcanism, complex sedimentary geology recording climate oscillations over orbital timescales, and preserved organic deposits potentially 4 billion years old. No other world in the solar system has all of those things simultaneously. But here is where the sentence breaks. Europa's simplicity at the surface may be a feature, not a bug. The liquid water ocean underneath is precisely simpler than Titan's surface. Simpler in the ways that are relevant to life chemistry. Life on Earth did not emerge in the most chemically complex environment. It emerged where the chemistry was just complex enough, and the conditions were just right. Titan may be too complex. There may be a kind of organic noise, an overwhelming accumulation of chemistry going in every direction simultaneously, producing a surface so covered in every possible precursor that the specific interactions needed for biology can't get traction. Earth's prebiotic chemistry happened in a world that was mostly rock and water. The organic inventory was limited. The chemistry had room to converge on specific pathways. Titan's organic inventory is not limited. It is enormous. Whether enormous organic inventory helps or hinders the emergence of biology, that is a question that cannot be answered from current knowledge of how life began. Because the knowledge of how life began is not sufficient to answer it. The complexity argument, fully looked at, yields this. Titan might be the most interesting world in the solar system, not because it is the most likely to have life, but because it is the world that will most directly test what chemistry can do over deep time without converging on biology. If life does not exist on Titan, when Dragonfly measures the surface organics and finds no biosignatures, no isotopic anomalies, no structures consistent with metabolism, then what Titan will tell us is what 4.5 billion years of prebiotic chemistry produces when all the ingredients are present except the conditions for life to start. That is a finding of immense importance, not a disappointment, a measurement. The measurement would say, this much chemistry, this much time, this much organic inventory, these temperatures, this solvent, and it didn't happen, which tells us something about what life requires that we didn't know before, the shape of what remains unknown. The inquiry needs to be honest here about a specific kind of uncertainty that is different from the others it has found. The uncertainty about Titan's weather, about how the methane cycle works, where the methane comes from, what the dune-building winds actually do, is an empirical uncertainty. It will be resolved, in part, by better data, more orbital observations, eventually more surface data. The answers exist, we haven't gathered them yet. The uncertainty about Titan's chemistry, about what 4.5 billion years of prebiotic chemistry has actually produced, is a different kind. It is not merely empirical, it is conceptual. We do not know what the outcome of long-duration, low-temperature, non-aqueous prebiotic chemistry looks like. We have no example of it. The only prebiotic chemistry we have ever observed in detail is the one on Earth, which ran in liquid water at higher temperatures and which resulted in life. We have no example of a prebiotic chemistry that ran and did not result in life. We don't know what that looks like. We don't know what chemical signatures it produces that are distinguishable from a chemistry that is just molecules reacting without biological catalysis or selection. When Dragonfly lands at Titan in 2034 and returns data about the organic chemistry of the dune sand and the crater material, scientists will look at that data and try to determine whether any of it is biological. They will look for isotopic ratios characteristic of life. They will look for molecular structures that are only produced by enzymes. They will look for a preponderance of one-handed molecules in what should be a 50-50 mix of left and right-handed forms. These are the biosignatures. They are what we know how to look for. They are all derived from Earth life. If Titan has chemistry that is neither Earth life nor simple non-life chemistry, if it has something in between, something that has been running long enough to produce order without being alive in the sense Earth life is alive, we may not know how to see it. Not because the instruments will fail, because we don't have a conceptual framework for what it looks like. That is not a criticism of Dragonfly. It is a statement about the boundary of the knowledge. The mission will find what it can find with the tools and frameworks it has. What it cannot find with those frameworks, what might exist at Titan that our categories don't describe, that is a limit that can be named here, but not resolved. The measurement is being designed before the framework for interpreting it is complete. That is not a failure. That is the normal state of science at its frontier. Dragonfly and what it won't reach. The Dragonfly mission is scheduled to launch in July 2028 and will arrive at Titan in 2034.
It is a rotorcraft, a helicopter-like vehicle designed to fly in Titan's thick, cold atmosphere, landing at one site, collecting data, then flying to another site tens of kilometers away. The plan calls for it to land in the Shangri-La Dune field, near the Huygens landing site, and eventually fly toward the Selk impact crater where ancient water ice and organic material may have been mixed together in the aftermath of an impact and then frozen in place, a preserved record of chemistry that the surface processes have since buried or erased elsewhere.
Dragonfly will not reach the seas. It will land in the equatorial desert, far from the polar liquid. It will measure chemistry, organics, prebiotic compounds, the signature of whatever processes have been running in the tholin-covered, methane-wetted surface for however long Titan has been this way. What it will not do is replace Huygens. It will add a different kind of data surface mobility, multi-site chemistry, direct atmospheric sampling from flight, but it will still be one craft, at one region, at one time in Titan's long seasonal year. The polar seas will remain, for some time after Dragonfly arrives, known only from above. The questions that most directly test the water cycle analogy: why no deltas? What are the magic islands? How does the sea stratify? Is there wave action? How does the river enter the sea? Those questions require something that lands in the sea, or at its edge, or measures it in a way that Cassini's radar could not. Those questions await the next mission after Dragonfly, which is not yet funded, not yet designed, not yet a commitment. A Titan submarine has been proposed in concept. A Titan lander at the polar shore has been proposed in concept. Neither exists beyond paper studies and advocacy documents. The seas of Titan, Kraken Mare, Ligeia Mare, Punga Mare, all the smaller northern lakes are, from the perspective of direct measurement, as unexplored as the deep ocean trenches of Earth were in 1950. We know they are there. We know their approximate extent and estimated depth. We know their composition at the level that orbital radar and infrared can constrain. We know they fizz, or might fizz, and that their coasts are moving northward, and that rivers drain into them without making deltas, and that something appears and vanishes in their waters without explanation. We have not touched them. We have not tasted them. We have not measured what is in them at the level of chemistry, what the inquiry found. The inquiry arrives here at something true. The accepted account of Titan's weather is the best account we have, built from real science, real data, real measurement. And it rests on a single landed data point from 2005, 13 years of orbital observation, and a vocabulary borrowed from a world that is nothing like the world being described. That is not a condemnation. That is the state of the knowledge. The vocabulary did what it needed to do. It made the thing visible. It made it possible to think about. It opened the questions that needed to be opened. But some of the most important questions on Titan right now, the delta absence, the magic islands, the methane budget, the cryovolcanism, the prebiotic inventory, those are questions the vocabulary can't generate from inside itself. They require noticing the places where the analogy breaks. They require standing at the edge of the word rain and looking at what the word doesn't cover. What the pressure of this inquiry found, not always where it was looking, the language problem and the data problem are the same problem. The vocabulary runs ahead of the evidence not because of carelessness, but because thought moves faster than spacecraft, and the language was the best available tool in the room when the images arrived. Titan's methane cycle operates simultaneously on 3 timescale storm events in Titan years, orbital liquid migration in tens of thousands of Earth years, geological methane replenishment in tens of millions, and no vocabulary currently holds all 3 without forcing one into the frame of the others. The 2 largest scientific questions about Titan, how the weather works, and what the chemistry has been making, are not competing questions but the same process seen at different timescales. And the shift toward the chemistry frame represented by Dragonfly is not a correction but an extension of a single inquiry. The clean simplicity of Titan's seas, their near-perfect microwave transparency, their low ionic content, is itself a finding that cuts against the ocean analogy, describing a sea that is more like a solvent reservoir than a reaction chamber, more like a cold storage medium than the reactive interior that Earth's oceans have always been. The magic islands remain unexplained, and their existence is a specific, persistent reminder that the frame being used does not fully account for what the data shows. The subsurface of Titan, the methane table near the poles, the deep liquid water ocean inferred from gravity, the possible cryovolcanic vents that might connect them is largely unmeasured, and most of the confident language about Titan describes a surface whose depth has not been reached. What turned out not to hold the implicit assumption that the methane cycle is self-sustaining the way Earth's water cycle is self-sustaining. The methane is being consumed. Something external to the cycle must replenish it. The cycle is not closed. It is being paid for by a geological process that has not been confirmed. Every raindrop that falls is a withdrawal against a reservoir whose balance and source remain unaudited. What the inquiry found that it was not directed toward. That Titan is the only place in the solar system other than Earth where all the preconditions for a question about the origin of life can be assembled simultaneously. And that the fact that a mission is launching there in 2028 represents not a confirmation that Titan has life, but an acknowledgement that the question can finally be asked with instruments capable of receiving an answer. What it reached but could not resolve, whether the chemistry running on Titan for 4.5 billion years has produced anything that our existing biosignature frameworks are capable of detecting. The measurement is being designed before the framework, for interpreting it is complete. The rain, at the end of all this. Return to the first word. The word rain on Titan means something fell from a cloud and hit the ground, and after all of this, here is what was underneath it.
It means a methane molecule, photochemically produced or cryovolcanically delivered to the atmosphere, evaporated from a polar sea in a season that lasts years, carried by a circulation pattern driven partly by orbital mechanics, condensed in a convective cloud above the equator during a rare storm event, forming a droplet 9 millimeters across, falling at 1 meter per second through an orange haze of complex organic particles, landing on a desert of dark tholin-covered dunes made from the organic fallout of billions of years of atmospheric chemistry, soaking into a substrate potentially saturated with a subsurface methane table, running off in an occasional channel toward a polar sea where it will join a body of liquid that may
whose shores are moving northward over thousands of years, and whose floor may carry submarine rivers of sediment that plunge downward without ever forming a delta. That is what fell from the cloud. That is what the word rain was carrying when it made the crossing from Earth to Titan. The word was not wrong. It arrived. It named the thing. It made the thing visible and thinkable and discussable across all the papers and press releases and late-night conversations about a world that almost no one will ever be closer to than an image on a screen. The word did its job, but the word was the beginning of the knowing, not the end of it. And the distance between the word and the thing it names, that distance, is where this entire inquiry has been living. The distance is specific. It is 9 millimeters wide and falls at 1 meter per second. It is millions of years between storms. It is a sea that fizzes without explanation. It is a shoreline that will be somewhere else in 50,000 years. It is 4.5 billion years of chemistry that has never been sampled. It is a world that has been named, but not yet met. What still isn't known and probably won't be settled from inside any inquiry this side of an actual visit. What it smells like, standing at the edge of Ligea Mare. Whether the light through the orange haze makes anything like shadow. What the slow methane rain sounds like on the tholin-covered sand. Whether there is anything in the dark below the surface of Kraken Mare that is organized enough to notice it is there. These are not rhetorical gestures. They are the literal shape of what remains unanswered, not by science's failure, but by its current reach, which extends to orbital radar and one 72-minute landing, and the instruments that will arrive in 2034, and no further yet. The rain falls at 1 meter per second, in a storm that comes to any given place once every several hundred years, on a world that is approximately where it has always been, doing what it has apparently always done, making what it has been making since before the first cell divided on Earth. We have a word for it.